Around 100 million years ago, Earth was a warmer, greener and stranger world. Shallow seas spilled over the continents, lush forests spread toward the poles, and giant dinosaurs wandered through humid valleys under brighter, heavier skies. The continents were on the move, the oceans were alive with ancient predators, and the planet's climate followed rhythms very different from today. If you enjoy peaceful journeys into Earth's deep past, please subscribe and share, and tell us in the comments which part of this ancient world are you most curious to explore. Thank you for watching. Now let's begin. Earth, around 100 million years ago, seen from far beyond the outer planets, is a small bright world circling the Sun in a path that is already very close to the one it follows in the present. It moves in an almost circular orbit, taking about the same length of time to complete one journey around its star as today, so its year is already familiar in duration, even though no humans yet exist to measure it. The planet also spins steadily on its axis, turning a little more quickly than it does in the modern age, so that each day is slightly shorter than the day now kept by precise clocks, although still long enough for stable cycles of light and darkness to shape weather and life over millions of years. Its axis is tilted by a little more than 20 degrees relative to the flat plane of its orbit, so the planet at this time still experiences seasons with shifting belts of sunlight over the course of the year, changing the distribution of warmth across low and high latitudes. From this distance, the solar system around it appears much as it does in later eras, with the same inner rocky planets and outer giant planets sharing the pull of the Sun and Earth, lying in the narrow band where liquid water can persist on its surface over long periods of time. Nothing in the geometry of the orbit suggests the dramatic one-time conditions of a rare catastrophe. Instead, the mid-Cretaceous interval is part of a long, stable episode in which the planet spends many millions of years in a warm greenhouse climate state, and its steady motion around the Sun provides a regular celestial framework for slow, geological and biological changes that accumulate over time. Closing the distance toward the planet, its overall appearance becomes clearer. Earth at 100 million years ago is still dominantly blue when seen from space, because broad oceans cover most of its surface. White swirls of cloud trace the paths of storms and jet streams through the atmosphere, and bright equatorial cloud bands assemble, where warm surface waters feed large-scale convection. Yet the pattern of colours across the globe is not quite the same as in the present. The contrast between equator and pole is more muted because the high latitudes are not capped by extensive permanent ice sheets. Instead of stark white ice caps stretching over polar seas and continents, the poles show a darker mix of open water, patchy seasonal sea ice at most, and cloud cover consistent with evidence that the polar regions in the mid-Cretaceous greenhouse world are considerably warmer than modern polar regions. These milder polar conditions allow forests and liquid water to persist, where later ages see tundra and thick ice. From orbit, this warmth translates into a planet whose coldest regions are less reflective and less sharply defined than the bright ice of recent geological time. The absence of large, highly reflective ice sheets means that the overall brightness pattern of the globe is governed more by cloud belts and by the distribution of continents and shallow seas than by brilliant white polar caps. Sea level at this time stands much higher than in the present, because the configuration of tectonic plates and extensive, relatively young ocean crust keep many ocean basins more elevated, leaving less room for deep water and allowing shallow seas to spread widely over continental margins. From space, these flooded continental edges appear as broad, pale fringes, where sunlight reflects from suspended sediment in shallow water, blurring the boundary between land and ocean. The arrangement of land masses is already distinct from the long-vanished supercontinent that once collected much of the planet's land into a single body. By the mid-Cretaceous, that former configuration has broken apart and the outlines of familiar modern continents are beginning to emerge, although their exact shapes and positions are still different from those of later times. From orbit, what stands out is not the detailed geometry of individual coasts, but the fact that many low-lying continental areas are drowned beneath warm epicontinental seas, while new ocean basins occupy the growing gaps between drifting fragments of crust. The atmosphere, though invisible as a gas, reveals itself through its cloud structures. Thick, bright cloud decks form over warm oceans where evaporation is strong, and over some belts where rising air cools and condenses into towering storm systems that wrap around the rotating planet. Other regions remain comparatively cloud-free, showing dark blue water or muted greens and browns of vegetated land beneath. Because the climate is warmer overall, the pattern of storm tracks and subtropical high-pressure belts differs in detail from the present, but from orbit the view is still that of a familiar, vigorously circulating atmosphere with moving systems of cloud, not a stagnant or alien shell. The reduced extent of continental ice lowers the number of intense temperature contrasts that would otherwise steer jet streams into sharp wavering paths, so the atmospheric circulation at this time is thought to be somewhat smoother and more zonal, flowing more directly from west to east in broad bands within each hemisphere. Over the course of a single rotation, the shifting cloud systems, moving shadows, and slow progress of the day-night boundary across the globe give a sense of a living planet in balance. Continents rotate into and out of daylight. The morning terminator sweeps over low-latitude oceans, and then across partially drowned lands, and the thin curved line of the atmosphere glows faintly where sunlight grazes it at the edge of the disk. Nothing in this distant view reveals the detailed forms of the plants and animals that inhabit the surface, but the large-scale signals of a warm ocean-dominated world are clear. Earth, at 100 million years ago, is recognizably the same planet that later supports human societies, but is also firmly in a greenhouse phase with high seas, warmer poles, and a different balance of land and water that would be immediately visible to a careful observer, watching from orbit over many successive days and years. The Earth around 100 million years ago presents a very different arrangement of land and sea from that seen in later ages, even though its basic size, shape, and position in the solar system remain the same. The single vast supercontinent that once gathered most of the land together has already broken apart, and the pieces now drift on the slowly moving plates of the planet's outer shell. From a global point of view, the surface is still dominated by ocean, but the pattern of continents and basins has changed enough to alter currents, climate, and habitats in ways that will persist for many millions of years. At this mid-Cretaceous time, the main continental fragments can still be grouped into two large families that descend from the old supercontinent. In the northern hemisphere lies a broad composite landmass, formed by what will become North America and Eurasia. In the southern hemisphere, a set of large blocks that include future South America, Africa, Antarctica, India, and Australia still carry the legacy of an older southern supercontinent, although several of these pieces are already beginning to drift apart. Between and around these landmasses lie wide oceans and complex marginal seas that give the globe a patchwork appearance of tongues of water cutting deep into continents and long peninsulas of land that reach into the sea. The Atlantic Ocean is no longer a narrow feature, as it was earlier in the Mesozoic era, but it is still far from its later width. A central rift and spreading ridge run roughly north to south, pushing the flanks of what will become Africa, Europe, and the Americas slowly apart. Along this growing ocean, the coastlines are irregular as high sea-level floods, low-lying margins, and produces broad continental shelves and shallow embayments. To the south, a narrower South Atlantic is opening between the separate blocks that will later become South America and Africa. The connection is not yet as broad and continuous as in later ages, but seafloor spreading already creates new ocean crust and allows water from the global ocean to move between what had once been joined lands. Farther east, the Tethys region occupies a huge belt that stretches from the western side of the future Mediterranean area across to regions that will one day include the Middle East, India, and parts of Southeast Asia. In this time slice, the Tethys is not a single simple gulf, but a complex realm of open ocean island arcs, microcontinents, and shallow platforms built of carbonate sediments. Fringing the northern edges of the southern continents and the southern edges of the northern continents, it forms a warm marine passageway that connects the young Atlantic with the older parts of the global ocean system. To the west of all these features, the Great Pacific Basin spreads over nearly an entire hemisphere. It is already a vast domain of deep ocean punctuated by island chains and volcanic arcs that sit above long subduction zones. The precise outlines of the Pacific coasts are different from those that will exist in later periods, but the general character of a wide, deep basin on the opposite side of the world from the Atlantic is already established. On the southern side of the globe, the lands that will later be recognized as Antarctica and Australia are still joined along much of their length, forming a combined high-latitude continent that fringes the Southern Ocean. Further north, the block that will become India is already drifting away from the African and Antarctic sectors of the southern land family. At this stage, it is a substantial island or small continent moving through the Tethys region toward the equator and the southern margin of Asia, although it has not yet collided to raise the mountain chain that dominates later maps. Africa and South America, though separated by an opening South Atlantic, still lie closer together than in later periods, and their outlines are less familiar. Wide shallow seas flood many lowlands on both continents, and broad river systems carry sediment from stable interior areas to passive continental margins where it is reworked by tides and waves. In the northern hemisphere, the continent that carries future North America is partly split by a great inland seaway that runs from the region of the present Arctic Ocean down toward what will later be the Gulf of Mexico. This western interior seaway divides the land into a western block and an eastern block, and transforms large areas of what will later be high plains into shallow marine environments. On the far side of this seaway toward the region that will become Europe, the land does not yet form one continuous block extending from the Atlantic deep into Asia. Instead, much of the area that will later host a dense network of countries is at this time a complex of peninsulas, shallow seas, and island chains that sit on submerged continental crust. Low-lying areas are often drowned beneath warm waters, while higher regions stand as emergent land supporting vegetation. Moving eastward across the super-region that will later be called Eurasia, the interior of the continent rises into older uplands and plateaus. Farther toward the margins, broad continental shelves step down into surrounding oceans. In several regions, long linear mountain belts have already begun to grow where plates converge, but many of the great ranges that will dominate later topography are still in their early stages. Between them lie foreland basins that may already be filling with sediment, or where near the coast hosting shallow seas. At a truly global scale, one of the most important aspects of the mid-Cretaceous layout is the amount of shallow epicontinental water that covers continental platforms. High sea level and the relative youth and buoyancy of much oceanic crust reduce the space available for deep ocean basins and encourage seawater to spread onto the edges of the continents. The result is a world map in which the distinction between land and ocean is softer than in later times. Many continental margins are fringed by very wide shelves, and interior basins in North America, Europe, Africa and Asia are flooded to form inland arms of the sea that link distant regions of the global ocean. Even in areas where land dominates, long estuaries and embayments extend far inland. When the globe at 100 million years ago is imagined as a whole, it is a planet of broken continents, widening young oceans, and a network of interior seas that knit together distant parts of the surface. The legacy of the old single supercontinent remains visible in the fit and alignment of coasts and in the shared geology of now separated blocks. But the world has clearly entered a new stage in which drifting plates and flooded margins create a more intricate and dynamic pattern of land and sea that will continue to evolve in the tens of millions of years that follow this mid-Cretaceous interval. In the middle part of the Cretaceous period, the solid outer shell of Earth is far from quiet. Beneath the oceans and continents, the planet's interior slowly releases heat, and that heat is expressed at the surface through a network of plate boundaries that reshape the crust over spans of many millions of years. At around 100 million years ago, the main outlines of the present plate system already exist, but the rates of motion and the distribution of spreading ridges, subduction zones and rifted margins differ from later times in ways that affect the height of the seafloor, the depth of the ocean basins and the building of mountains on land. The lithosphere, which is the rigid layer made up of crust and uppermost mantle, is broken into large plates that carry the continents and the ocean floors. Where these plates move apart, molten rock from the mantle rises and cools to form new oceanic crust. Where plates converge, older pieces of ocean floor sink back into the mantle, and the overriding plates crumple, uplift, and thicken to form mountain belts. In the mid-Cretaceous world, the total length of active mid-ocean ridges is great, and several parts of the global ridge system are producing new crust at relatively fast rates by geological standards, in some places on the order of several centimetres per year. This brisk production of new ocean floor means that much of the crust beneath the oceans is comparatively young and still relatively warm and buoyant. As a result, the average depth of the ocean basins is shallower than in times when more of the seafloor is old and cooled. Because the oceanic crust sits higher in the mantle when it is warm and young, the volume of the ocean basins is effectively reduced, and seawater spreads out more widely across the edges of the continents. From a global perspective, these processes at mid-ocean ridges are a major reason why sea level stands so high at this time, helping to maintain the flooded continental margins and inland seaways described in the broader paleogeographic picture. Along the great mid-ocean ridges themselves, the topography is rugged but systematic. At the ridge axis, a line of volcanic highs marks where new crust is added. Away from the axis on either side, the seafloor steps down as it cools, contracts, and becomes denser. Magnetic stripes frozen into basaltic lavas record alternating directions of Earth's magnetic field through time, and in the mid-Cretaceous part of the record, there is a long interval in which the field does not reverse. This so-called superchron later helps geologists to map the age structure of the seafloor, but in this ancient moment it is simply one expression of a strong and stable global magnetic field. Above some segments of the ridge system and in other oceanic regions, gigantic outpourings of basaltic magma have built thickened patches of crust known as oceanic plateaus. The Ontong Java region, the Kerguelen Domain in the southern Indian Ocean, and the early Caribbean Plateau are examples of large igneous provinces that form in the wider Cretaceous interval. Many of these plateaus either formed recently by 100 million years ago, or are still evolving through sporadic eruptions. Their crust can be tens of kilometres thick, much thicker than typical oceanic crust, and they stand high on the seafloor as broad swells or domes that later interact with subduction zones and continental margins. The creation of these enormous volcanic structures indicates that at least in some parts of the mantle, hot upwelling plumes are delivering large amounts of melt to the base of the lithosphere. In combination with the busy mid-ocean ridge network, this enhanced magmatism contributes to the high global volume of young buoyant ocean crust that characterizes the mid-Cretaceous tectonic system. On the margins of the major continents, subduction zones define long arcs where oceanic plates descend beneath continental or intra-oceanic plates. In what will become Western North America, an oceanic plate that will later be called the Farallon Plate is already sliding beneath the edge of the continent. Far inland from the trench, the overriding plate is shortening through a system of thrust faults that stack slices of crust on top of one another to build a broad mountain belt often referred to as the Sevier orogenic system. The deformation at this time is mostly concentrated near the margin, and the later phase that will lift deeper parts of the continent into high plateaus has not yet begun, but the groundwork for the long mountain chain is being laid. Farther south along the western margin of South America, a similar style of subduction-related mountain building is active with volcanic arcs and fold and thrust belts rising above the down-going slab. Around the margins of the Tethys realm between the northern and southern continental families, numerous arcs and small collision zones rim the oceans. Microcontinents and fragments of earlier crust move toward and sometimes collide, with the larger plates adding material to their edges and thickening the continental crust. In the regions that will one day host parts of southern Europe, the Middle East and Central Asia, these convergent processes are in stages of development that precede the dramatic uplift of later better-known ranges, but even at 100 million years ago they are already shaping long belts of uplifted and deformed rock. At the same time, other parts of the continents are stretching rather than shortening. In the South Atlantic region, rifting continues to open new oceanic corridors between the land masses that will become South America and Africa. Similar extensional processes have already created or are in the process of creating narrow ocean basins and broad rifted margins in other parts of the globe, including areas that will later host the Indian Ocean. In these zones, the continental crust thins as it is pulled apart. Normal faults break the crust into blocks, and eventually, once the stretching has progressed far enough, magma rises to create new oceanic crust and a young spreading ridge. Thick piles of sediments derived from nearby land are deposited in the subsiding rift basins and on the newly formed continental shelves, building the foundations of future passive margins. Vertical motions of the crust, driven both by the weight of growing mountain belts and by deeper flow in the mantle, also influence the arrangement of highs and lows on the continents. The inland seaway that cuts across what will later be North America, for example, occupies a region where the lithosphere is flexed downward under the load of the western thrust belt and where mantle-driven subsidence further lowers the surface. Elsewhere, broad domes or swells gently raise parts of the continents, altering river gradients and drainage patterns without necessarily forming sharp peaks. When the tectonic system at 100 million years ago is viewed as a whole, it is a world in which plate boundaries are widespread and active, mid-ocean ridges are long and productive, several enormous oceanic plateaus rise above the surrounding deep-sea floor, and multiple continental margins host broad orogenic belts. The detailed geography of mountain ranges and rifts varies from region to region, but the common element is that the solid Earth is continuously renewing its surface through a combination of spreading subduction, collision, and extension. These processes have already broken apart the earlier supercontinent and are now maintaining a high-standing oceanic crust and a complex relief of uplands, basins, and submerged platforms that set the stage for the climate patterns, sea levels, and habitats of the mid-Cretaceous world. The atmosphere of Earth around 100 million years ago is a familiar but subtly different envelope of air surrounding the planet, a thin continuous shell that controls how sunlight and heat move between space, the surface, and the oceans. It is still dominated by nitrogen, which makes up the bulk of the air, and oxygen, which supports complex life on land and in the sea, but the balance of greenhouse gases is not the same as in later ages. Evidence from rocks, fossils, and the chemistry preserved in marine shells points to levels of carbon dioxide that are several times higher than those of the modern world. In many reconstructions, carbon dioxide reaches values in the range of roughly 1,000 parts per million or more during portions of the mid-Cretaceous interval, rather than the few hundred parts per million of recent pre-industrial times. This additional carbon dioxide does not change the fact that nitrogen and oxygen remain the main components of the air, but it does strengthen the greenhouse effect, trapping more of the outgoing heat that would otherwise radiate to space and helping to maintain a warm climate across the globe. Other greenhouse gases, such as water vapour, also play important roles. Because the surface is warmer on average, more water evaporates from the oceans and from wetland surfaces, loading the lower atmosphere with moisture. Water vapour is itself a powerful greenhouse gas, so its increase reinforces the warming driven by carbon dioxide. Methane may also contribute, although its levels and variability through the mid-Cretaceous are less certain than those of carbon dioxide. In addition to gases that warm the planet, the atmosphere contains aerosols, tiny particles and droplets that influence how sunlight is reflected or absorbed. Volcanic activity is vigorous in the wider Cretaceous interval, and eruptions inject ash and sulfur-bearing compounds into the air. Some of these substances form short-lived particles that brighten clouds or scatter sunlight, producing regional cooling for limited times. Over longer spans, however, it is the sustained high greenhouse gas concentrations, not short pulses of volcanic dust, that best describe the average state of the atmosphere at this time. The vertical structure of the atmosphere is broadly similar to that of the present. Closest to the surface lies the troposphere, the lowest layer in which most clouds and weather systems form. Here, temperature generally decreases with height. As air rises, expands and cools. Above it lies the stratosphere, a more stable layer where ozone absorbs ultraviolet radiation from the sun, and where temperature first stops decreasing with height and then begins to increase. Higher still are the mesosphere and thermosphere, very thin realms where only a small fraction of the total mass of the atmosphere resides. In the mid-Cretaceous world, these layers remain present, controlled by the same basic physical laws. What changes are the details of temperature and circulation within them. In the troposphere, warm sea surfaces and high humidity give rise to vigorous convection in many low and mid-latitude regions. Large cloud systems build and decay in repeating cycles, as warm, moist air rises and cools, forming towering cloud masses that release rain and transport latent heat upward. Because the poles are much warmer than in later ice-rich ages, the contrast in temperature between equator and pole is reduced. This weaker gradient influences the position and strength of the jet streams, the high-altitude bands of fast-moving air that circle each hemisphere. Climate models and geological evidence together suggest that in the mid-Cretaceous greenhouse state, some aspects of the atmospheric circulation, including the Hadley cells that carry warm air from the equator toward higher latitudes, are reorganized. The zone where dry air descends may be shifted, and the belt of subtropical high pressure may contract, changing the distribution of arid and humid regions compared with later climates. Within the lower atmosphere, the concentration of oxygen is thought to be broadly comparable to that of the modern era, though estimates vary, and some intervals in the Cretaceous may have somewhat higher or lower values. Oxygen remains abundant enough to support extensive wildfires in many landscapes, as shown by charcoal and other fire-related traces in the rock record, and it continues to sustain active metabolisms in large animals on land and in the oceans. The presence of widespread forests, both at low and at high latitudes, indicates that plants are thriving under this combination of oxygen levels, warm temperatures, and plentiful carbon dioxide. The air also carries a range of trace gases produced by life and by geological processes, including compounds released by soils, vegetation, plankton, and volcanic activity. These trace substances can influence cloud properties and chemical reactions in the atmosphere, though their precise concentrations in the mid-Cretaceous are less tightly constrained than the broad pattern of high carbon dioxide and warm humid air. Another important aspect of the atmosphere at this time is its interaction with incoming sunlight. Higher carbon dioxide on its own does not greatly alter the amount of solar energy reaching the top of the atmosphere, since that is controlled mainly by the sun's brightness and by the orbital path of the planet, both of which are similar to those of later times. Instead, the key difference lies in how that energy is stored and redistributed. With reduced permanent ice and snow cover, the surface reflects less sunlight back into space, especially at high latitudes, so more solar energy is absorbed. Warm oceans and vegetated continents take up this heat, and the moist atmosphere efficiently transports it through winds, storms, and large-scale overturning. The result is a climate system in which the air, though composed largely of the same gases as in later ages, behaves in a way that keeps the planet ice free at the poles and maintains relatively small differences in average temperature between equatorial and polar regions. Across seasons and across latitudes, the mid-Cretaceous atmosphere acts as a thick, dynamically moving intermediary between the steady output of the sun and the slowly changing surface of the Earth, shaping the patterns of clouds, rainfall and heat that the oceans and continents experience at around 100 million years ago. In the world of 100 million years ago, the climate system is firmly in a greenhouse state, and this character shapes almost every aspect of the planet's surface conditions. The absence of large, long-lived ice sheets at the poles, the high concentration of greenhouse gases in the atmosphere, and the configuration of continents and oceans together create a warm, humid Earth, with relatively gentle differences in average temperature between low and high latitudes. At a broad scale, the amount of solar energy reaching the top of the atmosphere is much the same as in later ages, since the sun has only slowly brightened over geological time, and the orbital path of the planet lies close to its present one. What changes is how that energy is stored and redistributed by air, water, and rock. High levels of carbon dioxide and water vapor in the air keep more of the outgoing infrared radiation from escaping directly to space. As a result, surface temperatures remain elevated across much of the globe, and the usual pattern of cold polar regions and temperate mid-latitudes is softened into a warmer, more even distribution of heat. In low latitude, oceans' sea surface temperatures reach values several degrees warmer than those of many later warm intervals, and warm currents carry this heat toward higher latitudes without encountering the sharp thermal barriers created by extensive sea ice. The poles, while still cooler than the tropics, are much milder than the deeply frozen poles of more recent Ice Age climates. In some high-latitude regions, mean annual temperatures stay above the freezing point of water, allowing soils, rivers and forests to persist through the year. The reduced difference in temperature between equator and pole weakens one of the key drivers of atmospheric circulation, the meridional gradient that sustains strong jet streams and storm tracks in cooler climates. As a result, the winds in the upper troposphere may follow more zonal paths with broad belts of westerlies flowing steadily around the planet rather than being sharply kinked and meandering. At the same time, the Hadley circulation cells that transport warm, moist air from the equator toward the subtropics may extend further poleward, redistributing heat and moisture over a wider latitudinal range. In the tropics, warm sea surfaces and intense solar heating power deep convection. Towering cloud systems build and collapse in repeating patterns, releasing heavy rainfall and feeding large-scale overturning of the atmosphere. The location and strength of these rising air masses are influenced by the distribution of continents and inland seas. Where broad, warm oceans lie beneath the path of the overhead sun, moisture-laden updrafts are frequent, forming belts of persistent clouds and storms. Where large land masses cross the tropics and subtropics, seasonal heating of the continents encourages monsoon-like circulations in which winds reverse direction over the year, drawing moist air inland at some times and favouring offshore flow at others. The presence of extensive epicontinental seas adds complexity to these patterns. Shallow, warm arms of the ocean that flood the interiors of continents store heat efficiently and can moderate seasonal extremes in nearby land areas. Regions bordering such seaways may experience long, humid, warm seasons with frequent rainfall and only modest shifts in temperature between the warmest and coolest months. In contrast, some interior continental zones that lie far from these water bodies and that fall under subsiding branches of the Hadley circulation can be relatively dry with clear skies and less frequent precipitation, though still warmer overall than comparable areas under later cooler climates. Storm systems in mid-latitudes do still develop, driven by remaining contrasts in temperature and by the meeting of different air masses, but their typical tracks and intensities differ from those of times when powerful polar fronts dominate weather. With smaller differences in average thermal conditions between warm and cool regions, the energy available to some types of baroclinic storms is reduced. Instead, large parts of the mid-Cretaceous climate system are dominated by steady moisture-rich flows and by broad regions of convective activity rather than by sharp frontal zones. Over high-latitude land and sea, the lack of lasting ice sheets means that snow cover is seasonal and transient. Winters at these latitudes are still dark for long periods because of the tilt of Earth's axis, so temperatures do drop and snow can accumulate during the coldest months. However, in many reconstructions, summers are sufficiently warm that snow and ice melt back, preventing the long-term build-up of thick ice caps. Forests extend much closer to the poles than in later ages, and they experience long summer days with low sun angles, but relatively mild air followed by winters of extended darkness and cool conditions that are less extreme than those under a polar ice regime. Over the oceans, warm surface waters reach farther toward the poles than in most later climates. Sea ice, if present at all in many mid-Cretaceous intervals, is likely limited to seasonal and regional occurrences rather than forming a permanent cap. This expanded reach of warm surface water supports vigorous evaporation, cloud formation, and precipitation at high latitudes, contributing to a hydrological cycle that is active over much of the globe. Overall evaporation rates are higher on a warm planet, and what evaporates must eventually fall somewhere as rain or snow. The pattern of this precipitation helps define the locations of deserts, grasslands, forests, and wetlands. In this greenhouse world, some traditionally dry latitude belts may receive more moisture because of altered circulation, while other regions, especially in continental interiors under descending air, remain arid. The global picture is not one of uniform warmth and humidity everywhere, but of a climate system that, while warm, still displays a mosaic of wet and dry, cloudy and clear, mild and more seasonal regions. Within this framework, shorter-term variations such as storms, droughts, and heavy rainfall events are superimposed on a background that is consistently warm over millions of years. Orbital cycles that change the distribution of sunlight between seasons and latitudes continue to operate slowly shifting climate zones and affecting the depth and timing of monsoons, the extent of shallow seas, and the boundaries between different vegetation types. Yet even as these rhythmic variations play out, the defining feature of the Earth at 100 million years ago remains its greenhouse character. High carbon dioxide, reduced permanent ice, warm oceans, and an atmosphere rich in water vapor together sustain a climate in which the poles are ice-free or nearly so, in which the equator to pole temperature gradient is modest, and in which the circulation of air and water maintains a comparatively gentle but thoroughly warm planet that supports dense, diverse life in the seas and on land. At around 100 million years ago, sea level stands high above many later benchmarks, and this raised ocean surface transforms the outlines of the continents into a patchwork of peninsulas, shallow gulfs, and broad inland waterways. The causes of this elevated sea level lie partly in the state of the oceanic crust, and partly in the slow breathing of the solid earth. Young warm seafloor produced at long active spreading ridges is thicker and more buoyant than old cooled oceanic crust, so it rides higher on the underlying mantle. When a large share of the global seafloor is in this youthful condition, the capacity of the deep ocean basins to hold water is reduced. The result is that the same total volume of seawater must occupy a smaller set of deep troughs, and the excess is forced outward and upward, flooding the edges of the continents. Over millions of years, changes in the volume of mid-ocean ridges, the creation of large oceanic plateaus, and the pattern of mantle convection all contribute to maintaining the high stand of the mid-Cretaceous seas. On the continents, this high sea level converts low-lying regions into shallow epicontinental seas, also called epiric seas. These are not narrow, steep-sided gulfs, but wide, relatively flat bodies of water that cover continental interiors to depths often measured in only a few tens or at most a few hundreds of meters. Their floors are former land surfaces that now sit just below the waves, and they receive sediment and nutrients from surrounding uplands and river systems. Because they are shallow-like, can penetrate their waters over large areas, supporting active communities of plankton, algae and benthic life on the seafloor. One of the best-known examples of such an inland sea at this time is the Western Interior Seaway that cuts across the landmass of what will become North America. In this interval, the seaway stretches from high northern latitudes down toward a broad embayment in the region of the later Gulf of Mexico. Its width varies along its length, but at its broadest it spans many hundreds of kilometers from the rising mountain belt in the west to the more stable Craton in the east. In some areas, chains of low islands and submerged banks break the surface into smaller subbasins, while in others the open water extends in an uninterrupted expanse from one shore to the other. This elongated sea forms a liquid corridor that links polar waters with subtropical domains, influencing climate-ocean circulation and the distribution of habitats across a large part of the continent. The Western Interior Seaway is not the only inland sea of the mid-Cretaceous. In what will later be Europe and the surrounding regions, many low-lying areas are also drowned beneath warm, shallow waters. The future North Sea region, parts of Western and Central Europe, and broad tracts of adjacent continental shelves host epicontinental seas that separate emergent land masses into a complex archipelago. Farther south and east segments of the Tethys realm reach onto continental crust, forming broad platforms where carbonate sediments accumulate and where water depth often remains shallow enough for waves and storms to stir the seafloor. Similar flooded interiors occur on other continents. Margins of Africa, South America and Asia all bear evidence of extensive shallow seas that at times penetrate far inland. Some of these are linked to global ocean connections, while others form more restricted embayments, partially enclosed by sills or rising blocks of crust. In every case, the position of shorelines is sensitive to modest vertical motions of the crust and to longer-term variations in global sea level, so over millions of years these seas advance and retreat, leaving behind stacked layers of marine and coastal sediments. The edges of these inland seas where water meets land form long, low gradient coastal plains. Here tides and waves rework the products of river erosion, building deltas, barrier islands and tidal flats along the shifting shoreline. Because the slope of the drowned surface is gentle, even small changes in sea level or in the supply of sediment can move the coastline landward or seaward over large horizontal distances. As a result, broad belts along the margins of the seas may alternate between fully marginal marine and non-marine conditions, through time preserving a record of repeated transgressions and regressions. Within the epicontinental seas themselves, the water column tends to be stratified in ways that differ from those in the open ocean. Rivers flowing into the seas deliver fresh water at the surface, while denser, more saline water from the open ocean can linger at depth, especially where exchange through inlets and straits is restricted. Wind and tidal mixing stir the upper layers, but complete overturning to the floor may be limited, particularly in deeper parts of the basins. Under some combinations of climate circulation and nutrient supply, the bottom waters of these seas can become low in oxygen. In such settings, organic material that sinks from the productive surface layer may escape full decay and accumulate in the sediments, contributing to the rich petroleum source rocks that some mid-Cretaceous strata now represent. Above these quiet, sometimes stagnant bottoms, sunlit surface waters support abundant planktonic life. Microscopic algae and other primary producers use dissolved nutrients and sunlight to build organic matter, which in turn supports populations of small swimming creatures, larger invertebrates, and fish. In some regions, carbonate-producing organisms such as calcareous algae mollusks and other shell-forming animals thrive, giving rise to thick packages of limestones and marls. In other regions, a greater influx of terrigenous sediment from nearby land masses leads to more mixed deposits of sand, silt, and mud, often interlayered with marine fossils. The presence of vast areas of shallow, warm water also influences the exchange of gases between ocean and atmosphere. Compared with the deep ocean, shallow seas can respond more quickly to changes in air temperature, humidity, and wind. Their surfaces act as efficient sites of evaporation, feeding moisture into the atmosphere and contributing to regional rainfall. At the same time, they take up and release carbon dioxide in ways that depend on temperature, biological activity, and water chemistry, linking them closely to the carbon cycle of the mid-Cretaceous greenhouse world. The geometry of inland seas and coastal embayments affects not only local climate but also the broader circulation of the oceans. Narrow straits and sills that connect interior basins to the open ocean can control the flow of water between them, setting up distinctive patterns of inflow and outflow, driven by differences in density, temperature, and salinity. In the western interior seaway, for example, connections to both northern and southern oceanic domains allow for the exchange of water masses that carry heat and salt along the length of the basin. Elsewhere, more restricted epicontinental seas may develop characteristic circulation systems that trap water for longer periods, making them more sensitive to local changes in climate and runoff. When the global pattern of these high sea level features is considered together, Earth, at 100 million years ago, appears as a planet in which boundaries between ocean and continent are blurred across many thousands of kilometers. Rather than solid, simple outlines of land separated by deep ocean, the mid-Cretaceous map shows belts of shallow water that lace through the continents and create extensive coastal environments. These environments, with their shifting shorelines, deltas, estuaries, and interior seas, provide a wide range of habitats for marine and coastal life. They also form the setting in which sediments, nutrients, and organic matter are moved, mixed, and stored, leaving a layered record that later scientists use to reconstruct the conditions of this ancient high stand of the seas. The global ocean, at around 100 million years ago, is a single continuous body of water that wraps around the planet, yet it is not uniform. Its character is shaped by the broken ring of continents, the broad flooded shelves, and the deep basins that lie between long mid-ocean ridges and scattered volcanic plateaus. In this greenhouse world, the ocean is warm from surface to considerable depths. Its circulation is somewhat slower and more layered than in many later climates, and its chemistry reflects both high carbon dioxide in the air and active exchanges of carbon and nutrients between water sediments and living organisms. At the surface, winds blowing across the sea set up broad patterns of currents. Near the equator, steady trade winds push warm surface waters westward in belts that circle the planet, piling water against continental margins and island arcs. In the subtropics and mid-latitudes, these winds and the rotation of the Earth combine to form large gyres with currents that sweep poleward along some coasts and return equatorward farther offshore. The exact shapes and positions of these gyres differ from later ones because the Atlantic is still narrow, The Tethys region is a wide, complex seaway, and the Pacific dominates one side of the globe, but the basic idea of wind-driven surface circulation is already in place. Where currents run along the edges of continents or across submerged plateaus, they can draw deeper, cooler water upward or push surface water downward, linking the top of the ocean to its interior. The warmth of the climate gives the surface ocean a thick, buoyant skin. In low and mid-latitudes, the upper layer of water is heated by strong sunlight and loaded with salt through evaporation, so it is both warm and often relatively saline. Beneath this surface layer lies a zone where temperature decreases more rapidly with depth, forming a broad thermocline that separates the warm, mixed upper ocean from the cooler waters below. Because there are no large permanent ice sheets to chill and densify surface waters at the poles, the formation of very cold, heavy deep water is limited compared with later Ice Age states. Instead, parts of the mid-Cretaceous deep ocean may be filled by waters that sink from mid-latitude shelves and marginal seas which are cooler than the tropics but still warmer than later polar waters. This pattern leads to a deep ocean that is comparatively warm and in many regions older in terms of how long water masses have been away from the surface. As these deep and intermediate waters travel through the interior of the ocean, they gradually lose oxygen to the respiration of organisms and the decay of sinking organic material. In a vigorously ventilated ocean, such loss is balanced by the supply of new oxygen-rich water from the surface. In the mid-Cretaceous, however, the combination of strong stratification, high biological productivity in some regions, and slower renewal of deep waters means that large parts of the interior can become low in oxygen. In the most extreme cases, dissolved oxygen is nearly removed, and the water becomes anoxic. When such low oxygen conditions extend over wide areas and persist for long intervals, they are known as oceanic anoxic events. During these events, which occur several times within the broader mid-Cretaceous greenhouse interval, large tracts of the deeper ocean and some epicontinental seas host bottom waters that cannot support many higher animals. Organic matter that sinks from the productive surface is not completely broken down, and is instead buried in the seafloor, giving rise to dark, organic, rich sediments that later geologists call black shales. The time slice around 100 million years ago lies within a span of several tens of millions of years when these events are relatively frequent. Some, such as those near the early and middle parts of the Cretaceous greenhouse, involve widespread deposition of black shales in the open ocean and on continental margins. Others are more regional. Even outside the peak of these events, parts of the water column, especially at intermediate depths in restricted basins, and inland seas may hold only limited oxygen, forming expanded oxygen minimum zones. Above these low oxygen layers, the sunlit surface waters are often rich in life. Warm temperatures and the steady supply of nutrients from rivers upwelling and the recycling of organic material allow phytoplankton and other microscopic producers to thrive in many regions, particularly along continental margins around seaways and above topographic highs on the seafloor where currents concentrate nutrients. These microorganisms form the base of food webs that support small zooplankton, larger invertebrates, fish and marine reptiles. Their remains, along with tiny shells made of calcium carbonate or silica rain, slowly down into the deeper ocean, where some are dissolved, some are consumed, and some are preserved in the accumulating sediments. The chemistry of seawater at this time reflects its role as a major reservoir in the global carbon cycle. High carbon dioxide in the atmosphere means that more carbon dioxide dissolves in surface waters than in cooler, lower carbon dioxide climates. This dissolved gas participates in a series of reactions that make up the carbonate system involving bicarbonate ions and carbonate ions. In the mid-Cretaceous seawater is still generally supersaturated with respect to the main forms of calcium carbonate that organisms use to build shells and skeletons, especially in the warm, shallow regions of shelves and platforms. However, the exact balance of carbonate and bicarbonate ions and the overall acidity differ from later states. The ratio of magnesium to calcium in seawater also changes over long timescales, as the rates of seafloor spreading and the composition of the crust evolve, influencing which forms of calcium carbonate are more stable, and which organisms are favoured as major builders of reefs and other carbonate structures. Nutrients such as nitrate, phosphate, and trace metals circulate through the ocean as part of a linked biological and chemical network. Volcanic activity, weathering of rocks on land, and the recycling of organic matter in sediments all contribute to the supply of these nutrients. During intervals of intense volcanism and rapid seafloor spreading, additional nutrients and trace elements may enter the oceans, stimulating productivity in surface waters. When combined with strong stratification that limits deep mixing, this can enhance the tendency for deep waters to become oxygen poor and can encourage the formation of extensive black shales. Over longer timescales, the burial of this organic material in low oxygen environments removes carbon from the short-term cycle and can gradually draw down atmospheric carbon dioxide, providing a slow feedback on climate. The geometry of the mid-Cretaceous basins also shapes the paths of major currents and the exchange of water between different parts of the ocean. The narrow Atlantic and the broad Tethys Seaway act as channels through which warm surface waters move between low and high latitudes, while the huge Pacific hosts wide gyres and complex systems of intermediate and deep currents. Epicontinental seas, such as the Western Interior Seaway, are not mere side branches. They form important connectors that allow distinct water masses from northern and southern sources to meet and mix. In some reconstructions, relatively salty warm waters from low-latitude Tethyan regions flow into such seaways, while cooler, fresher waters from higher latitudes enter from the opposite end. Where they meet, density contrasts and bottom topography guide the formation of layered currents and internal fronts. Through these pathways, heat, salt, and nutrients are redistributed across the globe. When all these elements are considered together, the mid-Cretaceous oceans appear as warm, stratified, and dynamic systems in which circulation and chemistry are closely tied to climate and tectonics. Surface currents driven by winds move heat and salt over thousands of kilometers, while a somewhat sluggish but still active deep circulation carries the imprint of past surface conditions into the interior. High carbon dioxide altered seawater chemistry and frequent intervals of widespread low oxygen shape how carbon and nutrients travel through the system and how much organic matter is stored in marine sediments. Within this framework, the oceans of 100 million years ago provide the physical and chemical setting in which marine life diversifies and flourishes in ways that are both familiar in their basic structure and yet distinct in detail from the seas of later ages. Around 100 million years ago, the edges of the continents are broad low and often drowned, so that the boundary between land and sea is a wide zone rather than a sharp line. High sea level allows shallow water to reach far inland along gentle slopes, and where that water finally gives way to exposed ground, wide coastal plains develop. These plains fringe epicontinental seas and open ocean margins alike, forming long belts of low relief that wrap around much of the fragmented land surface of the mid-Cretaceous world. In many regions, the coastal plain begins at a shoreline that is not a steep cliff, but a very gradual rise from shallow water through tidal flats and marshes to slightly higher ground. The gradient from sea to interior is so gentle that over tens or even hundreds of kilometers, elevation changes only by tens of meters. Here, the interplay of tides, wave storms, and river discharge shapes a mosaic of sandy beaches, barrier islands, tidal channels, and mudflats. During calmer weather, fine sediment delivered by rivers settles in protected bays and lagoons. During storms, waves and currents cut new inlets, move barrier islands, and spread sheets of sand across the lowlands. The Western Interior Seaway, which cuts across what will become North America, is bordered on both its western and eastern margins by such coastal plains. On the western side, close to a rising mountain belt, rivers draining steep uplands carry large volumes of sand, silt and mud toward the seaway. As these rivers slow on reaching the low ground, they build deltas that step out into the shallow water. Delta fronts host channels that split and rejoin, while further landward floodplains and coastal swamps occupy the quieter parts of the plain. On the eastern side of the seaway, where the interior of the continent is more stable and the relief is lower, rivers follow longer and more meandering courses. Their valleys are broader, the slopes are gentler, and the resulting coastal plain is an even more expansive lowland, where fine sediments and soils accumulate over long periods. Similar coastal plains line the margins of many other epicontinental seas of this time. Across regions that will later become parts of Europe, for example, low-lying platforms are repeatedly flooded and exposed as long-term sea level trends and local subsidence shift the shoreline landward and seaward. Where water covers the platform, carbonate muds and shallow marine sand are laid down. When the shoreline retreats, coastal and fluvial deposits overlie these marine layers. Over millions of years, such alternations build thick successions of sediments that record a history of shifting coastlines. On the southern continents, including the future Africa and South America, the story is similar in its broad outlines but different in detail. Along some margins, large deltas prograde into shallow seas, creating wedges of sand and mud that thicken toward the ocean. Elsewhere, more sheltered embayments host quieter coastal systems, with tidal flats and lagoons protected by low barrier islands or carbonate banks. In the Tethys realm, where warm clear waters flood broad platforms, coastal plains often pass laterally into tidal flats and very shallow subtidal zones rich in carbonate-producing organisms. There, the transition from land to sea can be marked by sabkha, like environments where repeated wetting and drying under warm arid or semi-arid conditions lead to the precipitation of salts and gypsum alongside carbonate sediments. Inland from the immediate shoreline, the coastal plain grades into a more purely terrestrial lowland. This zone is dissected by river systems that flow toward the epicontinental seas and open ocean margins. Because the relief is low and the landscape is near base level, rivers tend to meander, creating sweeping bends that migrate slowly across their floodplains. During high flow periods, water overtops the banks, depositing layers of silt and clay on the surrounding land. Over repeated floods, this process builds natural levees and broad floodplain surfaces. In low points on the plains, standing water persists for long periods, forming swamps, marshes, and shallow lakes. In many mid-Cretaceous basins, conditions on these floodplains favour the accumulation of organic matter. Where groundwater remains near the surface and decomposition is limited by waterlogging peat, can build up, and over geological time this peat is compacted and transformed into coal. Such coal-bearing layers are often interbedded with fluvial and shallow marine sediments, reflecting the shifting balance between land and sea in these low-lying regions. Farther inland, but still within reach of the influence of coastal base level, the plains rise only gently toward interior plateaus and uplands. The warm, generally humid climate of many of these coastal lowlands supports weathering of bedrock and the formation of thick soils. On stable parts of the plains, long-term chemical weathering can produce deep, fine-grained regoliths rich in clays and iron oxides. On more dynamic surfaces closer to river channels, younger, less developed soils form on frequently reworked alluvium. The surface pattern is one of interlocking belts, river channels, and their immediate sandy banks, muddy floodplains, swampy depressions, and slightly higher, better drained interfluves. Toward higher latitudes, coastal plains around epicontinental seas experience long summer days and dark winters because of the tilt of Earth's axis, but the warmth of the greenhouse climate and the moderating influence of nearby shallow seas keep temperatures milder than in later ice-rich times. Snow may fall in winter and cover the lowlands for part of the year, yet it tends to melt back in the warm seasons, preventing the long-term build-up of ice. The result is a seasonal but not deeply frozen regime in which river discharge, sediment transport and soil processes follow annual cycles tied to light and temperature rather than to extreme cold. Along some margins where the influence of subtropical high-pressure belts is stronger and the descending branch of atmospheric circulation dominates coastal plains, can be drier with fewer perennial rivers and more ephemeral streams that flow only after seasonal rains. In these regions, wind may play a larger role in shaping the lowlands, moving sand into local dune fields, or reworking exposed muds on dry flats. Even so, the proximity of the sea means that moisture is never completely absent, and coastal fogs, sea breezes and occasional storms bring water inland. The constant background of geologic change also leaves its mark on these plains. As mountain belts rise or subside, as oceanic plateaus modify basin depths, and as mantle flow subtly lifts or lowers continental blocks the height of the land relative to sea level shifts. Over millions of years, these movements cause coastal plains to migrate. Areas that are coastal at one time may later lie beneath shallow seas, while old seafloors may be uplifted and stripped of their marine cover to become new lowlands. Through all these transformations, the coastal plains, lowlands and inland shores of the mid-Cretaceous world remain the broad transition zones where material and energy pass between continents and oceans. Sediments, nutrients, dissolved ions and organic matter all move through these gently sloping surfaces, binding together uplands, inland basins, epicontinental seas and open ocean, in one continuous system of erosion, transport and deposition that underpins both the geology and the future fossil record of this greenhouse Earth. Far from the immediate influence of breaking waves and tidal currents, the interiors of the continents at around 100 million years ago are dominated by broad lowlands in which rivers, lakes and extensive forests share the landscape. Relief is generally gentle across wide areas because many mountain belts are still in relatively early stages of growth, and long eras of erosion have smoothed older uplands into subdued forms. Where the ground lies only modestly above the drowned coastal margins and inland seas, humid air from the oceans can travel far inland without crossing high barriers, and the warm greenhouse climate allows wooded vegetation to flourish over vast regions of the lowlands. In these settings, river systems occupy the lowest parts of the surface. Large trunk rivers fed by many tributaries wind across the plains in sweeping bends, their channels migrating slowly sideways as they erode one bank and deposit sediment on the other. During periods of higher discharge, they spill onto their floodplains, filling backwater lakes and swamps with muddy water and fresh layers of silt and sand. Over time, abandoned loops of channel become oxbow lakes, and networks of shallow ponds and wetlands lace the lowlands. Sediments laid down in these settings form thick packages of fine-grained material, interbedded with coarser channel fills and with organic rich layers that mark long-lived marshes and peat-forming swamps. Covering and surrounding these river-bound lowlands are forests that in many places still show the imprint of older plant groups, even as newer ones are spreading. Conifers are prominent components of many mid-Cretaceous forests. Tall trees belonging to families related to Araucarians and other ancient conifer groups form the upper canopy in a range of climates from warm temperate to subtropical and even polar regions. Their trunks are straight and often widely spaced, and their crowns carry dense clusters of scale-like or needle-like leaves that intercept much of the incoming light. At their feet grow lower tiers of vegetation made up of ferns, horsetails and a variety of seed plants that occupy the understory. In some floodplain forests, open woodlands dominated by conifers, ferns and shrubs occupy stable surfaces that are only rarely disturbed by major floods, while younger, more frequently flooded ground is colonized by faster-growing plants that can tolerate burial by fresh sediment. At the same time, flowering plants are becoming increasingly important in these lowland landscapes. Angiosperms have appeared earlier in the Cretaceous, and by around 100 million years ago are diversifying into a range of forms that occupy understory and river margin habitats. Many early flowering plants are relatively small trees, shrubs or herbs that form thickets along stream banks on recently disturbed ground and in gaps within the conifer canopy. Their leaves often show shapes and venation patterns suited to warm, well-lit environments, and they may complete growth and reproduction more quickly than many of the older gymnosperm lineages. Enclosed forests of some floodplains flowering plants build dense understories beneath conifer canopies, intercepting light that filters through the upper branches and contributing to a more stratified vegetation structure. This mix of long-lived conifers and more opportunistic flowering plants produces forests that are neither fully modern nor entirely ancient in character. The overall appearance is one of layered productive woodlands in which new plant strategies are taking hold within a framework still dominated in many places by older tree families. Climate plays a central role in sustaining these forested interiors. In many low and mid-latitude regions, warm temperatures and abundant moisture support evergreen or seasonally evergreen vegetation. Rain falls frequently enough that soils rarely dry out completely for long periods, and transpiration from dense canopies returns large amounts of water vapour to the atmosphere, reinforcing local humidity. In some belts under the descending limbs of large-scale atmospheric circulation cells, conditions are drier and more seasonal, leading to more open woodlands or savanna-like mosaics in which trees share the landscape with shrubs and low herbaceous vegetation. Even there, however, the overall greenhouse warmth ensures that growing seasons are long and frost is rare, allowing plants to maintain active metabolisms through much of the year. At higher latitudes, including regions that sit within polar circles, forests also cover extensive tracts of lowland and gentle upland terrain. Here, conifer-dominated stands with an undergrowth of ferns and flowering plants endure long periods of summer daylight and extended winter darkness. The absence of large ice sheets and the relative mildness of the greenhouse climate mean that, although winters are cool and snow can accumulate, mean annual temperatures are often above freezing in many coastal and near-coastal areas. Trees in these polar forests must cope with unusual light regimes as much as with temperature-adjusting growth and leaf retention to cycles of continuous summer light and winter night, rather than to sharp thermal extremes. Across the forested lowlands of both hemispheres, soils develop under the combined influence of climate vegetation and parent material. On stable upland surfaces and older parts of the plains, deep weathering breaks down rock into thick profiles of clay, rich material sometimes stained with iron oxides that lend warm colours to the subsoil. On floodplains and younger terraces nearer rivers, soils are thinner and less developed, built on repeated layers of fresh sediment delivered by periodic flooding. In waterlogged depressions, organic matter accumulates faster than it decays, building peat that may eventually be buried and altered into coal. Charcoal fragments in some of these deposits testify to the presence of wildfires, indicating that lightning strikes and perhaps volcanic activity ignite vegetation under certain combinations of dryness and fuel abundance. Fire in turn influences forest structure, favouring some plant types that can resprout or regenerate quickly after burning and clearing patches in which flowering plants and other pioneers can spread. Lakes and wetlands nested within these lowlands add further variety. Some occupy abandoned river channels or subsiding parts of the plains, while others pond against subtle structural highs or volcanic landforms. Their margins host belts of aquatic and semi-aquatic vegetation, including ferns, horsetails, and flowering plants adapted to standing water. Fine sediments settle on their floors, preserving leaves, wood, and other plant remains that later provide detailed snapshots of mid-Cretaceous vegetation. Together with the fossilized wood preserved in floodplain deposits, these records show that forest productivity is high in many regions, with trees growing quickly under favorable temperature and moisture conditions. When the forested interiors and river-bound lowlands of this time are considered as a whole, they appear as extensive dynamic systems in which water sediment and organic matter are constantly cycled between rivers, soils, and vegetation. The landscapes are neither static nor uniform. Channels shift position, floodplains migrate, and local relief evolves as subsidence, uplift, and erosion operate over long timescales. Taken together, this describes a world where across much of the continental interior, warm, humid air, gently flowing rivers, and diverse layered forests combine to create a continuous, interconnected set of lowland environments that support rich terrestrial life and lay down thick archives of wood leaves, soils, and channel deposits for future geologists and paleobotanists to study. Away from the low coastal plains and river-bound interiors, the continents of Earth around 100 million years ago include broad tracts of drier ground, upland plateaus, and chains of active volcanic terrain that together give the mid-Cretaceous land surface a varied and uneven character. The greenhouse climate softens temperature contrast between equator and pole, but it does not erase differences in moisture relief or tectonic activity, so that belts of seasonal or persistent aridity, high-standing mountain fronts and volcanic arcs punctuate the otherwise warm world. In the subtropical latitudes of several continents, the descending branches of the large-scale atmospheric circulation favour regions in which rising air and frequent rainfall are replaced by subsiding drying air. Under these belts, the land tends towards semi-arid or arid conditions, even though the background climate is warm. Inland basins in parts of what will later be Asia, North Africa, and central parts of other land masses host landscapes where rainfall is limited and evaporation is strong, so that soils accumulate carbonate nodules, salt-rich layers, and other signs of water stress. In some basins, networks of sand dunes and wind-shaped surfaces record the action of persistent dry winds that move sediment in large cross-bedded packages. Intervening lowlands and closed basins collect ephemeral lakes and playa flats that fill briefly after seasonal rains and then dry down, leaving behind layers of evaporate minerals and mud-cracked surfaces. Even in these drier belts, however, the greenhouse warmth ensures that cold is rarely severe, so vegetation adapted to limited water occupies many slopes and valley floors. Shrublands, open woodlands, and sparse grasses or other low plants cover portions of these interior plains, drawing moisture from infrequent rain, groundwater, or runoff from surrounding uplands. At the margins of the great inland seas and along some continental corridors, there are zones where gradients in rainfall and topography give rise to mosaics of more humid and more arid habitats. In these transition areas, rivers that rise in distant highlands may cross otherwise dry country, supporting strips of gallery forest and floodplain vegetation along their banks, while leaving the interfluves in more open drought-tolerant cover. Over long periods, such rivers incise into their beds or wander across broad fans, redistributing sediment derived from the uplands. The higher parts of the continents, where mountain belts are actively rising above the cretonic cores, present a different face. Along the western margin of the landmass that will later become North America, convergence between an oceanic plate and the continent drives a long-lived system of subduction and crustal shortening. Inland from the oceanic trench, the overriding plate thickens as slices of crust are stacked, raising ranges that in this mid-Cretaceous interval form a broad, rugged hinterland. Their exact heights are uncertain, but they stand sufficiently high to influence climate, create significant relief, and shed large volumes of sediment eastward into the adjacent foreland basin and inland seaway. Similar processes operate along the western edge of the southern continent that will become South America, where an active volcanic and tectonic margin raises mountains and supplies ash lava and eroded detritus to coastal and interior basins. Around the Tethys realm, the picture is more complex but follows related principles. Arcs of volcanoes and uplifted belts define the boundaries between the northern and southern plate families, and blocks of crust that once lay in oceanic settings are moved towards scraped onto or under thrust beneath the larger continents. Even where the relief does not yet match that of later famous ranges, these mid-Cretaceous uplands stand as elevated terrain relative to surrounding lowlands. Their slopes host different climates and hydrological regimes, from those of the coastal plains with more intense rainfall on some windward faces and rain-shadow effects on others. Snow can still fall on the highest peaks in cooler seasons, even under greenhouse conditions, and meltwater feeds rivers that descend into the inland basins. Many of these high-standing belts are tied to long chains of volcanoes. Above subduction zones, magma generated in the mantle, and lower crust rises to feed stratovolcanoes and broader volcanic fields. In the region corresponding to the later western North American Cordillera arc, volcanoes align roughly parallel to the trench. Some eruptions build steep cones of andesite and related rocks, while others spread sheets of ash and pumice over wide areas. Farther inland, smaller volcanic centres and related intrusions add complexity to the tectonic fabric. Along other margins around the ancient Tethys volcanic arcs, form island chains and coastal ranges that ring portions of the seaway. Their activity sends ash high into the atmosphere during explosive eruptions, and lays down thick local deposits of lava and pyroclastic material that later weather into soils and are reworked by streams. In addition to these arcs, parts of the wider mid-Cretaceous interval witness very large-scale volcanic events linked to mantle, upwelling known in hindsight as large igneous provinces. Some of these, like the Greater Kerguelen region in the southern oceans or the high Arctic plateau magmatism, have both submarine and subaerial expressions. On or near continental margins, the flood-like outpouring of basaltic lava builds thick piles of rock that can stand as broad plateaus once eruption ceases and erosion gets to work. At around 100 million years ago, parts of these provinces are newly formed or still active, while others have already begun to be sculpted by rivers and waves into stepped highlands and dissected uplands. The surfaces of these volcanic plateaus and lava fields present stark but not lifeless landscapes, with fresh basalt scattered volcanic cones and networks of young valleys that carry water away toward lower ground. Weathering of volcanic rocks both in arcs and in plateaus releases nutrients such as phosphorus and trace metals into soils and streams. These substances travel downstream to support productivity in lowland and coastal ecosystems, while the rough, uneven surfaces of the uplands themselves host plant communities adapted to rocky substrates, thin soils, and in some regions cooler or more seasonal moisture regimes. Outside the most tectonically active margins, there are also high plateaus and broad uplands on more stable parts of the continents. These elevated surfaces may be remnants of older mountain belts worn down by long erosion, or flexural uplifts associated with deep earth processes. Their relief is less dramatic than that of the active origins, but still sufficient to separate climate zones and river systems. On some of these plateaus, weathering produces thick lateritic soil profiles under warm, moist conditions, although parts of them may lie in drier belts where vegetation is more open. Rivers rising on these uplands carve valleys and transport material toward the lower plains, and over long spans they can incise deeply, leaving stepped landscapes where ancient surfaces are preserved on interfluves above younger canyon floors. Across all these settings, from deserts and semi-arid basins to high volcanic arcs and stable uplands, the mid-Cretaceous greenhouse conditions still make themselves felt. Mean temperatures are generally higher than in many later periods, and frost is confined mainly to higher elevations and seasonal extremes. Yet the combination of global circulation patterns, plate configurations and topography ensures that water is not distributed evenly. Some regions, particularly in the interiors of continents under subtropical subsidence or in rain shadows cast by rising ranges, experience long dry seasons or multi-year droughts, while other regions on windward slopes and near warm seas receive abundant rainfall. The result is a continental surface that at the scale of a hemisphere shows a rich variety of terrain, upland ridges and plateaus, active volcanic belts, broad interior basins with deserts and seasonal lakes, and the earlier described lowlands and coastal plains. Together these elements form the physical framework on which the later sections of this narrative will place the mid-Cretaceous terrestrial ecosystems, showing how plants and animals fit into and respond to the drylands, uplands and volcanic landscapes of this ancient warm Earth. In the northern mid-latitudes of Earth around 100 million years ago, broad belts of land to either side of the great inland seas support rich terrestrial ecosystems that reflect the warm greenhouse climate and the varied topography described earlier. Along the western and eastern shores of the long interior seaway that divides the northern continent and across comparable lowlands, fringing the young Atlantic and the Tethys realm, wide floodplains, gentle uplands and coastal terraces are covered by forests, open woodlands and wetlands. These landscapes lie far enough from the equator that the sun's height in the sky and the length of day still change through the seasons, yet they are close enough, and the climate is warm enough that frost is rare and snow where it falls is brief and seasonal. The result is a set of environments that in average conditions are warm temperate to subtropical, rather than cold or strongly seasonal, with long growing periods and sufficient moisture in many regions to maintain dense vegetation. On many of these northern lowlands, the plant communities still show a strong influence of older gymnosperm lineages, while also incorporating a growing presence of flowering plants. Conifer trees form much of the canopy in many forests, especially on well-drained ground and on slightly higher terrain. These conifers include forms related to Araucarians and other long-lived families with tall, straight trunks and crowns that intercept light high above the ground. Cycads ginkgo, like trees and tree ferns, also contribute to the woody and shrubby layers in places, especially on slopes and in less frequently disturbed stands. Beneath and between these older elements, flowering plants are spreading into a wide variety of niches. In some northern coastal plain and river margin settings, local floras already show a high proportion of angiosperm leaves and pollen. Many of these early flowering plants are small trees and shrubs with broad leaves, while others are herbs that occupy disturbed soils along rivers, lake margins and forest gaps. Together, gymnosperms and angiosperms create layered forests, in which light, humidity and temperature vary from canopy top to forest floor, providing many potential habitats for animals and smaller plants. In low-lying areas near inland seas and along major rivers, swamp forests and wetlands extend across the landscape. Here water stands for long periods in shallow depressions and peaty soils accumulate under woods and thickets. Conifers with buttressed roots seed ferns, and early flowering swamp plants grow in these waterlogged settings, while ferns and horsetails occupy the understories and the banks of small channels. Fallen wood and leaf litter build thick mats that in some of the quietest parts of these wetlands are preserved as accumulating peat that will be buried and transformed over geological time into coal. Slightly higher ground carries mixed forests in which conifers and flowering trees share the canopy, and understories include shrubs, ferns and herbaceous angiosperms. On the better drained parts of the plains, especially nearer to drier belts or rain shadow zones, vegetation becomes more open. Woodlands with scattered conifers and flowering trees stand over a ground layer of low shrubs and herbs, and in some places patches of more steppe, like vegetation, appear with grasses and grass-like plants among the early angiosperms sharing space with low gymnosperms and ferns. Across these terrains, large herbivorous dinosaurs form a conspicuous part of the faunal assemblage. In many northern mid-latitude regions, medium to large, ornithischian dinosaurs occupy a variety of feeding roles. Iguanodontian and early hadrosauroid forms browse and graze on vegetation, ranging from low shrubs to higher branches using beaked mouths and batteries of teeth to process tough plant material. In some areas, early members of the group that will later give rise to fully developed duck-billed dinosaurs move in groups across floodplains and coastal terraces, following belts of preferred vegetation that flourish along rivers and around wetlands. Lower to the ground, stocky armoured dinosaurs such as ankylosaurs and nodosaur-like forms move more slowly through forests and open woodlands, cropping low vegetation and relying on bony plates and in some taxa tail clubs as defence against predators. In certain parts of the northern continent, sauropod dinosaurs also remain present at this time. Titanosaur and related lineages inhabit more open floodplain and upland settings, where their great size and long necks allow them to reach foliage unavailable to other herbivores. Together, these herbivorous dinosaurs shape vegetation patterns by browsing, trampling and transporting seeds and spores on their bodies and in their digestive systems. Predatory dinosaurs share these landscapes, occupying a range of sizes and ecological roles. Large theropods, including Allosauroid and Carcharodontosaur-like forms in some regions, and early members of the Tyrannosauroid lineage in others, hunt or scavenge the larger herbivores. Their long skulls, serrated teeth, and strong hind limbs make them effective pursuers and carcass openers. Smaller theropods, including agile dromaeosaur and troodontid lineages, stalk smaller vertebrates, nest contents and perhaps invertebrates in forest margins, on floodplains and along the shores of rivers and lakes. Feathered forms within these groups, together with early birds, occupy perches in trees and move through the air over clearings and water bodies. The avian component of these ecosystems includes toothed long-tailed early birds, as well as more derived forms with shorter tails and more modern wings, many of which likely exploit insects, small vertebrates and plant material. Along rivers, lakes and wetlands, a diverse assemblage of semi-aquatic and aquatic vertebrates occupies the interface between water and land. Crocodilians bask on banks and lurk in quiet channels, ready to feed on fish, smaller dinosaurs and other animals that venture to the water's edge. Turtles inhabit ponds, slow-moving streams, and marginal bays of inland seas, some adapted to freshwater and others to more brackish environments. Amphibians, including frogs and salamanders, live in and around the shallows where they breed in pools and feed on invertebrates. Fish communities in the rivers and lakes include both primitive and more derived ray-finned groups, some of which move between freshwater and nearby marine or brackish settings as part of their life cycles. Small terrestrial vertebrates add further layers of complexity. Mammals of this time are mostly small nocturnal or crepuscular animals, many of them insectivorous or omnivorous. They live in burrows, in leaf litter, or in trees feeding on insect seeds, and perhaps small vertebrates or eggs. Lizards, and in some regions early snakes, occupy warm, sheltered spots on the ground, and in vegetation preying on insects and other small animals, together with an abundant and diverse insect fauna that includes beetles, flies, wasps, and early pollinating groups. These small vertebrates connect plants, detritus, and larger animals in intricate food webs. In the plant communities themselves, the rise of flowering plants is beginning to alter ecological relationships, even if conifers still dominate many canopies. Early angiosperms on these northern lowlands may already rely on insects for pollination in many cases, and their seeds and fruits change the resources available to invertebrates and small vertebrates. Pollination and seed dispersal interactions, though only partially recorded in the fossil record, are already present as processes that tie together plants, insects, and vertebrates. Spores and pollen from both gymnosperms and angiosperms, shed into the air and washed into lakes and floodplain ponds, settle into sediments alongside leaves, wood dinosaur bones, and the remains of small animals. Over time, these deposits build up a detailed archive of the mid-Cretaceous vegetation and fauna of the northern mid-latitudes. When the northern mid-latitude terrestrial ecosystems of this interval are considered as a whole, they appear as broad, warm, and biologically complex regions in which forests, open woodlands, rivers, wetlands, and low uplands are linked by the movements of water sediment and organisms. Large herbivorous dinosaurs, large and small predators, crocodilians, turtles, amphibians, birds, mammals, lizards and insects all share the space created by conifer and flowering plant-dominated vegetation. The overall picture is one of long-lived productive landscapes that, under the influence of a warm equable climate and changing plant communities, support a rich and varied terrestrial biota across the northern mid-latitudes of Earth around 100 million years ago. In the southern hemisphere at around 100 million years ago, the land that once formed the southern supercontinent is broken into large pieces, yet its ecosystems still share a family resemblance shaped by common paleogeographic roots and by the warm greenhouse climate. The blocks that will become South America, Africa, India, Antarctica, Australia, and the partially submerged continent that later will be called Zealandia, stand at a range of latitudes from tropical belts to the high southern polar circle. Across this span, forests, open woodlands, river systems, and drier interior basins host communities of plants and animals that parallel those of the northern mid-latitudes in some ways, but also show their own distinctive combinations of species and environmental conditions. At southern mid-latitudes on the large continental pieces, broad lowlands and gentle uplands support extensive forests and woodlands. In many parts of what will become southern South America and southern Africa, warm temperate to subtropical climates prevail with only modest seasonality and temperature, and rather generous rainfall in regions influenced by westerly winds or nearby epicontinental seas. On these lands, conifer trees form a major component of the canopy. Families related to southern conifers, later known as podocarps, and araucarians grow as tall evergreens, their trunks rising straight and their crowns forming dense, dark canopies. Cycads and tree ferns are common in some understories and on slopes, while a diversity of ferns and horsetails occupies moist ground along streams and in low hollows. Flowering plants which have been spreading since earlier in the Cretaceous are now established in many of these southern ecosystems. Shrubby and herbaceous angiosperms occupy disturbed ground river margins and forest gaps, while small to medium-sized flowering trees weave into the lower and middle canopy layers. Their leaves and reproductive structures are adapted to the warm, often humid climates, and many of them likely rely on insects and perhaps small vertebrates for pollination and seed dispersal. Along some coasts and around inland basins, swamp forests and wetlands occupy poorly drained ground. Their peat accumulates beneath stands of conifers, seed ferns, and flowering swamp plants, interlayered with silts and sands deposited by fluctuating rivers and lakes. Moving toward the interior of some southern continents, especially where atmospheric circulation and topography reduce rainfall, drier environments appear. Parts of what will later form the interior of Africa and of the southern land masses host semi-arid basins with seasonal rivers, ephemeral lakes, and more open vegetation. In these regions, conifers may be confined to better watered valleys and slopes, while more drought-tolerant shrubs, early flowering plants and low gymnosperms dominate upland flats and gentle hills. Soils here can be rich in carbonate nodules and show signs of periodic drying and re-wetting. Yet even in these drier belts, the greenhouse climate and the absence of prolonged severe cold allow plant growth for much of the year, supporting diverse animal life. As latitude increases toward the southern polar region, the structure of the land changes again. The southern polar zone at this time is occupied largely by the linked landmass of East Gondwana, which joins what will later become Australia, Antarctica and Zealandia. These continents straddle the region around the South Pole, yet they do not carry great ice sheets. Instead, much of their lowlands and gentle uplands are covered by temperate forests that must cope not with extreme cold but with unusual rhythms of light and darkness. In these polar forests, summers bring long periods of continuous or nearly continuous daylight, while winters bring extended darkness, yet the mean temperatures remain mild enough for trees to maintain living tissues year-round. Fossil evidence from later but closely related intervals within this greenhouse world, together with reconstructions for the mid-Cretaceous, indicate that these southern polar forests are dominated by evergreen conifers, especially in contrast to the more mixed evergreen and deciduous canopies of the northern high latitudes. Tall podocarp and araucarian conifers form the backbone of the canopy, extending in belts that reach to very high latitudes near the polar circle. Beneath them, a rich understory of ferns, horsetails and flowering plants occupies the forest floor. In some settings, deciduous elements may appear with trees that shed leaves to cope with winter darkness, but many of the conifers retain foliage year-round, taking advantage of the long summer days to sustain photosynthesis under high carbon dioxide and moderate temperatures. The ground in these polar forests often remains free of permafrost, though seasonal freezing of soils and winter snow cover can occur especially inland and at higher elevations. Tree growth rings preserved in fossil wood from parts of Antarctica and southern high-latitude regions indicate alternating periods of rapid growth and slower or paused growth that match the annual cycle of light and temperature rather than the deep, prolonged freezes of later Ice Age conditions. In lowlands near coasts and along rivers, peat-forming swamps and wet soils add to the diversity of plant habitats, while on slopes and better-drained ground thicker, better aerated soils support dense roots and deep weathering profiles. Within these southern forests and woodlands, dinosaurs and other vertebrates form a complex fauna adapted to the local climates and light regimes. In the mid and high latitude southern lands, herbivorous dinosaurs include small to medium-sized ornithopods that browse on low vegetation and perhaps on certain shrubs and small trees. Their skeletons and teeth indicate adaptations for feeding on plant material, and bone beds in some high-latitude deposits suggest that at least some species live year-round in these regions rather than merely migrating through. Larger herbivores, including sauropods and perhaps larger ornithischians in more temperate southern belts, occupy floodplains and open woodlands where their tall necks and large bodies give them access to higher foliage. Predatory dinosaurs share these southern ecosystems. Medium to large theropods, some related to Allosauroid and other large-bodied lineages, hunt or scavenge the bigger herbivores in mid-latitude regions, while smaller theropods, including agile, possibly feathered forms, move through the undergrowth and along the edges of rivers and lakes. In the high southern forests, fossil remains show that small theropods and a range of ornithopods live in environments that experience long polar nights and cool, but not frozen temperatures, indicating that these animals tolerate months of darkness and seasonal change in food availability. Early birds and bird-like theropods add an aerial component to the fauna perching in trees, feeding on insects, small vertebrates, and perhaps plant material and moving between forest gaps and river corridors. Crocodilians, turtles, and amphibians inhabit rivers, lakes and wetlands on the southern continents, much as they do in the northern hemisphere. In higher latitude settings, some crocodilian relatives may be more cold-tolerant than later tropical forms, using river channels and sheltered pools to survive cooler seasons. Freshwater fish occupy lakes and streams, and invertebrate life, including insects, with links to flowering plants, fills the water and air. On the forest floor and in the leaf litter, small mammals, lizards, and invertebrates live in burrows under logs and within soils connecting detritus plant seeds and higher trophic levels. The seasonal cycle in these southern polar and near-polar ecosystems is shaped more by light than by extreme temperature. During the long summer days, plant productivity is high, with evergreen conifers and deciduous plants alike, capturing carbon under prolonged illumination. Animals take advantage of this abundance to grow, reproduce, and build reserves. During the extended winter, darkness temperatures fall, but in many coastal and lowland areas remain above levels that would cause intense sustained freezing. Plants slow or pause their growth, and animals shift behavior, perhaps relying on stored food, reduced activity, or movements to slightly milder microhabitats. The forest remains standing, and snow cover where it develops is seasonal rather than permanent. When the southern Gondwanan and polar land ecosystems of this mid-Cretaceous interval are seen as a whole, they form a continuous but varied band of life stretching from subtropical lowlands to high-latitude forests around the South Pole. Evergreen-dominated polar woods, mixed conifer and flowering plant forests at mid-latitudes drier, interior basins with more open vegetation and swampy lowlands around epicontinental seas are all part of a single interconnected system. It is a system in which the greenhouse warmth of the planet allows forests to reach into polar latitudes, in which dinosaurs, early birds, mammals, and a host of other animals occupy niches from river floodplains to upland slopes, and in which the seasonal rhythm of light and darkness rather than deep cold defines the boundaries of life on the far southern lands of Earth around 100 million years ago. In the shallow seas and coastal margins of Earth around 100 million years ago, the warm greenhouse climate and high sea level combine to create broad marine regions that support dense, diverse communities of life. Along the flooded edges of the continents and across the submerged platforms of the Tethys realm, and young Atlantic extensive belts of shallow sunlit water stretch for hundreds of kilometres. Water here is generally clear and warm, often remaining above 20 degrees Celsius through much of the year, and light penetrates to the seafloor over wide areas. Within this broad illuminated zone, a range of seafloor communities develops from soft-bottom faunas on muddy and sandy substrates to exuberant reef-like build-ups made by organisms that can bind or secrete carbonate. On many warm, low-latitude shelves, the roles that later ages assign mainly to corals are in this time often taken over by unusual bivalve mollusks known as rudists. These shellfish, some shaped like elongated cones, and others like irregular cylinders or small pillars, anchor themselves to the sea floor or to one another, building dense thickets and mounds in waters that are often only a few tens of meters deep. Their shells, composed largely of calcium carbonate, grow upward and outward as the animals filter feed from the passing water, capturing plankton and suspended particles. As they die and their shells accumulate, the structures they create can rise into substantial bioherms and banks that baffle currents, trap sediment, and form complex three-dimensional habitats. Other organisms occupy the spaces within and around these rudist build-ups. Corals, though still present in many mid-Cretaceous seas, often play a more limited role than in some later tropical reef systems, forming patchy frameworks that grow alongside or on top of rudist-dominated mounds in certain regions. Encrusting algae, sponges, bryozoans and serpulid worms also contribute to binding and stabilizing the carbonate framework. Between these larger structures, the seafloor is carpeted in places by a mix of sand, gravel and shell debris, with burrowing mollusks, crustaceans and echinoderms living within and above the sediment. Sea urchins, starfish, and brittle stars move over the substrate, feeding on algae detritus and small invertebrates. In somewhat deeper parts of the shelf, beyond the most vigorous wave action, but still within the reach of light, communities shift toward those adapted to quieter water and finer sediment. There, delicate bivalves, brachiopods in some regions, and various small crustaceans live partly buried in mud and silt, while thin beds of carbonate mud accumulate between periods of more active current flow. Burrowing worms and other infauna churn these sediments, mixing organic matter into the upper layers and ventilating the pore spaces. Microscopic plankton, including calcareous nanoplankton and other single-celled algae, thrive in the warm nutrient-bearing waters near the surface. When they die, their tiny shells fall like continuous rain onto the seafloor, gradually building fine-grained carbonate deposits that can blanket large areas of the shelf and upper slope. Above these shallow seafloors, the water column is busy with swimmers and drifters. Schools of bony fish move through the midwaters, feeding on plankton and smaller fish. Some are small, streamlined forms that travel in shoals near the surface, while others are larger predators with strong jaws and teeth, adapted to cutting flesh or crushing shells. Sharks already diverse by this time patrol. These seas as well, ranging from small benthic species to larger open water hunters. Their skeletons, made largely of cartilage, rarely preserve completely, but their teeth shed continually throughout life, accumulate in the sediments, and later record their presence in large numbers. Hovering among this finned life are a variety of cephalopods. Ammonites with coiled external shells partitioned into gas-filled chambers drift and swim through the water, adjusting buoyancy with changes in the mixture of gas and fluid in their chambers. Different species occupy different depths and ecological niches, some nearer the surface, and others living deeper in the water column. Straight or gently curved belemnites, whose internal bullet-shaped rostra often fossilize, also inhabit these seas likely as active predators in the midwaters. Together, ammonites and belemnites form a key part of the diet for many of the larger marine predators of the time. In the more open parts of the shallow seas and over adjacent outer shelves, large marine reptiles are prominent. Plesiosaurs with broad bodies, strong flippers, and in some forms long flexible necks swim through the upper waters, surfacing periodically to breathe air. Shorter-necked relatives with larger heads focus more on powerful bites, pursuing swift prey in open water. By around 100 million years ago, mosasaurs, the large marine lizards that will dominate many late Cretaceous seas, are emerging and diversifying in some regions, although their greatest spread comes somewhat later. These animals possess elongate bodies, strong tails and limb modifications that transform their forelimbs and hindlimbs into flippers. Their jaws carry rows of sharp teeth suited to seizing fish cephalopods and smaller reptiles. Sea turtles glide through these same waters, using their flippers to migrate along coasts and across open stretches, while feeding on seagrasses, invertebrates, or jellyfish depending on species. Over the deeper continental slopes that descend from the shelves into the basins, light levels decrease, temperatures fall slightly, and communities shift as pressure increases. The upper slopes still receive some filtered light, and fine rain of organic material and microfossils settles from the surface layers above. Benthic foraminifera, small-shelled protists living on or within the sediment, are abundant, and their species composition varies with depth and oxygen levels. Larger invertebrates such as certain echinoderms, crustaceans and mollusks persist, where oxygen remains sufficient, but in zones where the oxygen minimum is particularly strong, animal life at the seafloor is sparse and laminated. Organic rich muds accumulate with few traces of burrowing. These transitions between oxygen-rich and oxygen-poor zones are not fixed. They shift with regional circulation productivity and longer-term oceanic anoxic events. but at any given time they create vertical and horizontal gradients in habitat conditions across the marine realm. Closer to shore in lagoons and protected arms of inland seas, marine and brackish conditions mingle. Here, salinity and temperature can vary more strongly from season to season, and even from day to day as river discharge evaporation and exchange with the open sea change. Organisms living in these marginal settings must tolerate such fluctuations. Some bivalves and gastropods specialize in brackish water, while certain fish and crustaceans move freely between fresh brackish and fully marine environments. Seagrass-like plant communities may appear in some sheltered shallow parts, stabilizing sediments and providing habitat for invertebrates and juvenile fish, though the exact timing and spread of true seagrass lineages is still an area of ongoing research. In many of these coastal and shallow marine settings, the interface between land-derived material and marine carbonates is sharp in some places and diffuse in others. Near the mouths of large rivers, plumes of suspended sediment and fresh water spread out over the sea surface, creating turbid zones where light penetration is reduced. Here, communities shift toward forms that can tolerate lower light and more variable salinity, and finer-grained, often darker sediments accumulate on the sea floor. Farther from river mouths, clearer water allows carbonate-producing organisms to flourish, and the sediments become dominated by shell fragments, algal debris and fine carbonate mud. The regional marine ecosystems of the mid-Cretaceous seen in this way include not only the open shelves and rudis banks, but also the gradients that connect nearshore brackish bays, inner shelves, outer shelves, and upper slopes. Across these gradients, the composition of the communities changes, yet the underlying physical setting remains one of warm, relatively stable temperatures in the upper water column, high sea level, that enlarges shallow marine domains and seawater chemistry that favours the precipitation of carbonate skeletons. The organisms that live here, from microscopic plankton to large marine reptiles together, form linked food webs that depend on primary production in the sunlit layers and that export organic matter into the depths. Their shells, bones, burrows, and biochemical traces are buried in the sediments as time passes, building the stratified record that will later allow geologists and paleontologists to reconstruct the intricate fabric of these mid-Cretaceous seas. On the margin of one of the broad inland seaways that crossed the northern continent around 100 million years ago, there is a quiet embayment where a shallow lagoon meets a low-forested shore. The inland sea extends far to the north and south, but here along this gentle recess in the coastline, the water is partly sheltered from the main body of the seaway by a chain of low sandbars and tidal shoals. The lagoon is only a few meters deep over much of its area, and its floor is a mix of fine mud-shell fragments and patches of clean sand, where currents have swept away the finer particles. The shoreline follows a very slight slope, so that from the water's edge the land rises only slowly into the trees with no cliffs or steep bluffs, only a fringe of wet ground that grades into slightly higher, better-drained soil beneath the forest. Twice each day, gentle tides move water in and out of the lagoon through narrow inlets, raising and lowering the surface by amounts that are small in absolute terms, but significant for the plants and animals that occupy the boundary between land and sea. When the tide is high, brackish water laps at the roots of trees and shrubs that grow close to the shore. When it falls, stretches of mud-flat and sandbar emerge glistening under the mid-Cretaceous sun. During calm weather, the water in the lagoon is clear enough that the pale bottom can be seen from the surface, especially near the shore. Light penetrates to the sediment, allowing thin films of algae and small rooted aquatic plants to grow in patches, particularly in the more sheltered corners where wave action is weak. Farther out toward the inlets, currents are stronger, and the bottom is scoured into ripples of sand that shift over time as tides and wind-driven flows rearrange the grains. The water is warm through much of the year, with temperatures near the surface comfortably above the threshold at which many modern temperate marine organisms are active. Salinity varies with distance from the river mouths that enter the lagoon and with the state of the tide. Near the mouths of small rivers and streams, the water can be only weakly salty, especially after heavy rains in the hinterland. Closer to the inlets that connect to the broader seaway, it is fully marine, and subtle density contrasts between fresher and saltier water help to shape the circulation within the embayment. Air above the lagoon is warm and often humid. During daylight hours, gentle breezes blow from the open water toward the land, carrying the smell of salt-wet vegetation and suspended organic matter. Clouds form and dissipate overhead as moist air rises from the warm surface building fair weather cumulus that sometimes grow into larger storm systems moving along regional wind belts. Rain falls at intervals sometimes as brief showers, sometimes as more prolonged events that swell the streams and rivers feeding the lagoon. At night, winds may reverse, flowing gently from the cooling land toward the water, while mists form in low spots along the shore. The forest that borders this lagoon is dense but not impenetrable. Closest to the water, the ground is often saturated and the vegetation reflects this persistent wetness. Low shrubby plants, some of them early flowering forms adapted to brackish soils, grow among the buttressed bases of conifer trees, whose roots anchor them in the soft substrate. Ferns and horsetails form a thick herb layer, their fronds and stems arching over tiny pools and channels that remain even at low tide. Farther inland by a short distance, the ground becomes more consistently firm, and the forest shifts to a mix of taller conifers and a growing number of deciduous and evergreen flowering trees. Their canopies overlap to form a continuous roof of foliage broken only by small gaps where older trees have fallen. Underneath, dappled light reaches the understory where shrubs, juvenile trees and ground ferns share space with rotting logs, fallen branches and a thick layer of leaf litter. The soils here are rich in organic matter and remain moist for long periods, though they drain better than the saturated band at the immediate shoreline. Along the narrow strip where the forest meets the lagoon, a variety of animals move between land and water. In the shallows, small fish dart among submerged roots and stems, feeding on plankton and invertebrates stirred from the sediment. Slightly deeper, larger fish and small marine reptiles patrol for prey, occasionally entering the lagoon from the main body of the seaway through the inlets. On the muddy flats exposed at low tide, burrowing invertebrates leave faint trails and mounds as they process the upper layer of sediment in search of organic matter. Shells of small bivalves lie partly buried, their owners drawing in water through siphons to filter food. At the water's edge, turtles rest on gently sloping banks sliding into the lagoon when disturbed and returning to bask when conditions are quiet. Crocodilians occupy the deeper channels and the mouths of streams, their bodies just below the surface, eyes and nostrils breaking the waterline as they wait in slow stillness for fish or unwary animals that come to drink. On the forest side of the boundary, herbivorous dinosaurs follow regular paths that lead from deeper within the woods down to the shore. Medium-sized ornithopods moving in small groups browse on low vegetation along the forest margin, and sometimes step onto the firmer parts of the flats when the tide is low, feeding on plants that grow in the zone of brackish influence. Their feet leave impressions in the soft ground, some of which will later be filled with sand or mud and preserved as trackways. In slightly more open patches near the water, armoured dinosaurs pass by at intervals slower and more solitary, using the cover of the trees and the varied ground to find ferns, cycads and low shrubs. Predatory theropod dinosaurs also visit this margin, though less frequently. Smaller agile forms move along game trails using the broken light of the understory and the cover of vegetation to approach flocks of smaller animals. Occasionally larger theropods pass near the lagoon, following the movements of the herbivores as they travel between feeding areas and water sources. Birds, both early forms with more primitive tails and more derived forms with shorter tails and stronger flight, move between the forest and the lagoon. Some perch in the branches overlooking the water, watching for fish or small invertebrates at the surface. Others hop along the shore, probing the mud for worms and small crustaceans. Insects are abundant in this interface zone. Dragonflies patrol the airspace over the water and the swampy ground, while beetles, flies, and wasps move among flowers, decaying wood and carcasses. Pollinating insects visit the flowering plants that have taken hold along forest edges and in sunlit gaps, while detritivores and scavengers help to break down fallen leaves and animal remains. Within the forest soil and the upper layers of lagoon sediment, countless smaller organisms from minute crustaceans to microscopic fungi and bacteria carry out the slow, continuous work of decomposition and nutrient recycling. Over the course of a typical day, the conditions in this coastal forest lagoon habitat change in subtle but important ways. The rising sun warms the air, and the surface waters increasing evaporation and the activity of many organisms. As the tide comes in, water covers more of the flats, bringing in fresh supplies of plankton and suspended particles from the larger seaway. As it recedes, it leaves behind moisture in the sediment and strands small pools where fish, invertebrates, and plant fragments are temporarily trapped before the next cycle. Rainstorms, when they pass, freshen the surface waters near the river mouths and deliver pulses of fine sediment and dissolved material from the hinterland. Between such events, the system settles into a quiet pattern of gentle currents, steady biological activity, and slow accumulation of sediment and organic matter. Through all these changes, the lagoon and its bordering forest remain part of a broader network of habitats linked along the seaway's margin. Animals move along the shore from embayment to embayment plants, disperse seeds and spores across river catchments, and water carries dissolved substances and fine particles from the land to the interior of the sea. The local scene, with its warm, shallow water, soft sediment, humid air, and mixed vegetation, is one small expression of the wider mid-Cretaceous world in which high seas, greenhouse climate, and evolving continental outlines combine to create countless such coastal habitats around Earth at about 100 million years ago. In the mid-Cretaceous world of around 100 million years ago, the large-scale patterns of climate geography and ecosystems are built from countless small interactions among organisms and between life and the environment. At the scale of an individual forest, clearing a lagoon margin, or a patch of shallow sea floor, these interactions leave traces in living tissues, in sediments, and in the chemistry of shells and bones. Over time, many of these traces are buried and preserved, providing fine-scale evidence of how plants and animals share space, obtain energy, grow, reproduce, and respond to the conditions of this greenhouse Earth. On a warm floodplain beside an inland seaway, for example, a stand of mixed conifer and flowering plant vegetation includes many small repeated exchanges between plants and insects. Flowering shrubs and low trees bear simple blossoms whose pollen and nectar attract beetles, flies, and early relatives of bees and wasps. As the insects move from flower to flower searching for food, grains of pollen adhere to their bodies and are carried between blossoms, allowing fertilization to proceed and seeds to develop. At the same time, wind carries clouds of pollen from the cones of nearby conifers, spreading the male gametes of these older lineages over a wide area. Some of this wind-borne pollen lands on the intended receptive structures of conifers, while much of it settles onto water soil and leaves, adding to the rain of microscopic particles that slowly accumulates on the forest floor and in nearby ponds and lakes. Leaves on many of these plants bear the effects of herbivory. Some show the smooth, rounded margins of leaves that have been fed upon by larger insects with chewing mouthparts. Others display fine networks of tunnels where the larvae of leaf mining insects have eaten their way through the inner tissues while leaving the outer layers intact. Still others carry small clusters of circular or irregular holes or patches of surface scraping where feeding has removed only the upper part of the leaf. These patterns those small record preferences and behaviours of different insect groups. Over time, damaged leaves that fall to the ground are incorporated into soils or muds. In some cases, leaves fall into quiet water, where they are buried quickly in fine sediment. When this happens under conditions that limit decay, both the outline of the leaf and the signs of feeding can be preserved as impressions, retaining a record of the interaction between plant and herbivore at the moment the leaf was shed. On open parts of the same floodplain, herbivorous dinosaurs feed in groups. As they move and feed, they strip foliage from shrubs and low branches, trample young plants underfoot, and break twigs and stems. Footprints pressed into soft mud along river banks and in shallow ponds record the passage of individuals and groups of different sizes. Some tracks are deep and broad, with clear impressions of toes and pads, while others are shallower or more fragmentary, altered by later water flow, or overprinted by the feet of other animals. In a few cases, trackways preserve sequences of steps that show stride length pace and changes in direction. Over time, many of these impressions are filled by sand or silt, and when the sediment hardens, the original footprint and its filling form a pair of complementary surfaces that capture a brief episode of movement across the landscape. In nesting areas on slightly higher ground, some herbivorous dinosaurs lay eggs in shallow scrapes or simple mounds. Clutches contain several to many eggs arranged in arcs or rings, or grouped in shallow pits depending on the species. The eggshells possess microstructures that can be seen when thin slices are examined in transmitted light, including layers of calcite crystals and networks of microscopic pores that would have allowed gas exchange between the growing embryo and the outside air. In some nesting horizons, eggs are preserved crushed in place, while in others scattered fragments of shell indicate that hatching or predation has occurred. Around and above these nests, bones and small traces of juvenile animals sometimes appear, hinting at the early stages of growth in the hatchlings and at the risks they face from predators and environmental stress. Predatory dinosaurs and other carnivores also leave fine scale marks on the remains of their prey. Bones of herbivorous dinosaurs preserved on floodplains in channels or in nearshore marine sediments often bear tooth marks in the form of grooves, punctures, or scrapes. Some of these marks match the spacing and shape of the teeth of large theropods, while others correspond to smaller carnivores or scavengers. In a number of specimens, evidence of healing around bite marks shows that some animals survive attacks and live long enough for bone to remodel, providing a record of both injury and recovery. In addition, arthropods and other scavengers leave their own traces on carcasses, including small borings into bone surfaces and gnawed edges where soft tissues once attached. Within the skeleton itself, microscopic features of bone record growth histories and responses to the environment. When thin slices of limb bones from dinosaurs are examined, they show networks of vascular canals and patterns of bone tissue that reflect rates of growth and the balance between rapid deposition and later remodeling. Growth marks that resemble lines or bands somewhat similar to growth rings in trees occur in many individuals. In some cases, these marks are spaced in a way that suggests cyclic variations in growth, perhaps linked to seasonal changes in food availability, temperature, or light, even within the overall warm climate of the mid-Cretaceous. In marine environments, similar fine-scale records accumulate. Shells of bivalves, gastropods, and ammonites grow by adding successive layers of calcium carbonate, and the thickness and composition of these layers can vary with environmental conditions. Growth lines on the exterior and internal banding reflect intervals of faster and slower shell deposition. At a finer level, the ratios of different forms of oxygen and carbon locked into the shell material provide information on water temperature and the chemical state of the ocean at the time each layer forms, even without detailed measurements. Changes in shell microstructure and the presence of repair scars where predators have damaged but not destroyed shells reveal episodes of stress and survival. Tiny planktonic organisms also leave microscopic tests and plates that contribute to the fine record. Calcareous nanoplankton produce minute plates that fall to the seafloor in great numbers, forming chalky sediments in some basins. Benthic and planktonic foraminifera build small chambered shells that differ in shape and wall structure, depending on depth, temperature, and other factors. Over time, the vertical and horizontal distribution of these microfossils within marine sediments records changes in water masses productivity and the expansion and contraction of low oxygen zones. In coastal lagoons and forest margins, sticky resin exuded from the bark of certain trees occasionally traps small organisms. Insects, spiders, bits of plant material, and even tiny feathers from feathered theropods or early birds can become embedded in these viscous droplets. If the resin hardens and is buried rather than decaying, it can be preserved as amber. Within such pieces, three-dimensional details of the trapped organisms remain, including delicate structures like antennae, wing veins, and fine hairs. Pollen grains, spores, and microscopic fragments of plant tissue also become incorporated, preserving associations between plants and the animals that live among them at a scale rarely captured by other fossil types. Below the ground surface in both terrestrial and shallow marine settings, burrows and other trace fossils provide further evidence of activity that is seldom preserved as body fossils. Simple vertical shafts, U-shaped tunnels, branching networks, and surface scrapes in sediments represent the work of worms, crustaceans, insects, and other invertebrates. The size, shape, and internal structure of these traces indicate the size and behavior of their makers, from deposit feeding in soft muds to more complex dwelling structures in firm grounds. Some burrows show lined walls or pellets suggesting careful construction, while others are more irregular, marking rapid movement through unstable sediment. Taken together, the small-scale anatomical features growth records trace fossils and microscopic remains preserved from this time slice of Earth history form a densely layered archive of community-level interactions. Each bite mark, leaf, mine, growth ring, shell, layer, pollen, grain, and burrow is a single instance of an organism interacting with its surroundings. When many such instances are combined in the rock record, they reveal patterns in how plants, invertebrates, vertebrates, and microbes use energy and materials, how they respond to seasonal and longer-term changes, and how they fit into the broader physical setting of the mid-Cretaceous greenhouse world around 100 million years ago.